Okay, thank you very much for the introduction and the invitation to speak. So today I'll talk about the geometry of some kind of modular spaces of local Galois representations. So I realize this is an algebraic geometry seminar. So like I'm a number theorist, so the kind of modular space I care about are largely motivated by number theory. So let's, if you have any questions or if you want me to clarify anything, please feel free to type in the chat or like unmute yourself and ask, because I may not always follow what's happening in the chat. Okay, so let me start with the kind of motivational background. So I'll fix a prime P and a number field F, and I let GF be the absolute Galois of the number field F. Then the kind of global Lagrange correspondence, or the Lagrange reciprocity conjecture, is this conjectural kind of bijection between the, I guess, algebraic automorphic reps of, say, GLN of the adels of AF. And this should correspond to, maybe let's call it pi. And this corresponds to like periodic kind of continuous representation of the absolute Galois group of F, which are geometric. Okay, so I will not, so before that, let me say, the word geometric here kind of stands for two properties. One is that it's unramified almost everywhere, which is a mild condition. And the second crucial condition is it should be de Rham at kind of at all place dividing V dividing P. So if I restrict to the decomposition group at a prime above P, it will satisfy some periodic Hodge theory condition called de Rham, which I'll come back to that later. So like, if you're not unfamiliar with what an automorphic representation is, it's can be taught as basically a kind of higher dimensional generalization of a modular form. So when n equals 2 and f equals q, algebraic kind of an algebraic automorphic rep for GL2, at least a large amount of them are just like modular forms for like congruent subgroups of SL2Z. And really an automorphic rep is like a bunch of those modular forms. And it turns out that inside an automorphic rep, you can take like a specific representative, and that corresponds to the condition of being an eigenform for all Hecke operators, which are like at a minimal possible level. And in this case, the condition that you correspond to would be, well, geometric, but also odd. So this corresponds to the fact that not all algebraic automorphic reps of GL2 AQ come from modular forms. There's a special class of non-holomorphic form that are also algebraic. So this is kind of like, so of course, like already the special case has kind of far-reaching consequences. Most famously, kind of Weil's proof of Fermat's last theorem was proceeding by actually like showing this bridge. And so, for example, if I take the kind of periodic tit module on an elliptic curve of Q, if I know this kind of reciprocity, I will kind of know there's a corresponding modular form. And basically, you prove Fermat's last theorem by showing that the corresponding, like a non-trivial solution of Fermat's last theorem will give an elliptic curve that corresponds to a modular form that doesn't exist. So it's kind of like useful to kind of have this kind of reciprocity conjecture, but that example also shows that it's really hard. And one reason you can think of why it's hard is because both sides are kind of just countable kind of, or discrete set in some sense. So that's because a global geometric Galois representation and kind of an automorphic representation are two very rigid objects, so they don't deform. So this kind of don't come, this has no moduli. And so it's very hard to kind of match two countably infinite collections in a meaningful way. So the most successful approach to attack this kind of reciprocity conjecture at present is the kind of approach using periodic deformation. And the basic idea is kind of like the following. So I'll kind of put that in a kind of diagram like this. So maybe I have an algebraic automorphic graph pi, think of a modular form, say. This should correspond by global long-lengths to the geometric, like global Galois representations. And as I mentioned earlier, both sides here are very rigid. They are kind of like countably kind of discrete sets. And so the idea is basically you think of this countably discrete set as basically special points in some larger kind of modular space, which you have a better chance of relating. And so this is why on the Galois side, this corresponds to restricting the global Galois representation to all the decomposition groups above P. So these are the local Galois reps. And on the automorphic side, the local avatar of an automorphic rep is like a representation of some periodic group. So this is kind of like some kind of restriction. Okay, so why is this helpful? So the key phenomena here is that there are a lot more local stuff, and the local stuff are much less rigid, and so there's actually moduli. There exists meaningful moduli of the local objects. Okay, so in pictures, you can think of the situation as like the global thing are kind of like dots. So these are the global. These are like automorphic rep or global Galois reps. They are kind of dots, discrete dots sitting out there in space. The local stuff are kind of like varying in nice kind of like geometric families. So, and I guess, so this is the arrow up here is kind of global long-lengths. And so this stuff down here is kind of supposed to be kind of periodic long-lengths. So there's a way you could try to relate kind of representations of periodic groups to local Galois representations. So, so the picture is I have a bunch of discrete dots on the global part, and they kind of dissolve into like continuous nice geometric families on both sides. And so it's easier to match kind of like moduli spaces than kind of like special points on it. So that's kind of the idea. So the reason this helps is because like if I have two moduli space, I can start think about like measuring their size in meaningful ways, like how much the dimensions are, and I can try to match them by say prove like say they have the same dimensions, they have the same kind of singularities and so on. So there are lots of geometric kind of maneuvers you can do once you actually have a meaningful moduli space instead of just points. So this is kind of like how it helps. And this kind of like this is carried out successfully in the so-called kind of Taylor-Wilds method, which is kind of basically an execution of this idea. Or like in Emerton's kind of approach to kind of proving the Fontaine-Mazer conjecture, kind of following this principle. Okay, so this approach is kind of like behind most of the success we have so far about Langland's reciprocity. Okay, so from kind of my description of the situation, like here, this picture, it's clear that in order to kind of carry out the strategy, we need kind of two basic ingredients. So one is we need to actually construct and understand the geometry of the moduli spaces. Understand the geometry of the moduli of the local stuff. Okay, so that's like these pictures here. And then the second is that you can match the local like the modular space of local stuff, but then you have to kind of like identify exactly how the global stuff sits inside it. So you need some kind of control. You need to control how to get the global stuff inside, or how to locate the global stuff inside this moduli. So in my talk, I will my goal will be to kind of like analyze this kind of ingredients on the Galois side. So goal will say something like I give the general kind of an introduction to the circle of ideas kind of performing this for the, say something about the Galois side. This. So that means that I want to describe a little bit about what kind of like modular space of local Galois representations one may want to consider, and also what kind of like properties one would, what kind of special loci one want to kind of investigate in order to locate the global geometric Galois representations sitting inside those. Okay, any questions? Well, I'm going to move on to. Okay, so let me now go to this. Let me now kind of work entirely on the kind of Galois side. And the basic setup will be I start with a periodic field, so finite extension QP with absolute Galois group GQ, and it has a ring of integers OK with residue field little k. All my representations are always kind of in some p-completed world. So I will fix a coefficient field E that's a large enough extension of QP, and it has ring of integers O, residue fields F, and uniformizer var pi. Although I think I most of the time forget and just write P. Okay, so it turns out that there are two different layers of kind of moduli of Galois representations one can investigate. So let me start with the classical theory. So this is largely initiated by Mazur, and it also has another name. It's called local Galois deformation theory. So this is in some sense, the kind of like the local or formal moduli of periodic Galois GK reps. So the setup is kind of like this. You have to fix at the outset a kind of mod P Galois representation. So a continuous map from GK to GLN F, a finite field. So and then it turns out it's rather easy to show that you can just classify like all liftings of these two Artinian O algebras. So this is classify all the lifts of my fixed rho bar to Artinian coefficient test rings, or more generally to complete local Noetherian O algebras. So let me make more space. I kind of Artinian. And so this object is called the universal lifting or deformation ring. So let me say lifting. And its structure is not so bad. The standard deformation theory is going to tell you that its cotangent complex or something is closely related to the Galois cohomology of K, which with question in the adjoint of rho bar, it's fairly simple to analyze using like just Galois cohomology kind of techniques. But so this would be deservedly called the local moduli of Galois representation, kind of near this rho bar. But as I said before, we don't just want a kind of moduli of local Galois representations. We also need kind of meaningful loci in it to kind of locate the geometric global Galois reps. And so for that, we also need like various kind of like quotients or like special loci inside this kind of like this moduli, this local moduli. And so what kind of locus is this? So these are the loci of, so I can put into quotation marks because I will explain this terminology now. Potentially crystalline or semi-stable. I will stick to crystalline GK rep with kind of like hot state weights lambda and inertial type tau. Okay, so whatever this adjective means, they are going to be some kind of periodic Hodge theory condition. So these are kind of like periodic Hodge theory type of conditions. And these are the conditions that are working only for the rational periodic representation on the rho from GK to like GLN QP bar. So note, it's very important to note where the coefficient of representation is. So this is for characteristic zero kind of Galois representations. Although my original rho bar was on F, and like the moduli problem that rho bar represents is for Artinian ring or more generally on complete local Noetherian rings. And the specific, the actual kind of meaning of this is that the kind of max spectrum, the maximal spectrum of the generic fiber of this can be identified with kind of like periodic, certain kind of periodic Galois representations. So namely those that have a lattice lifting rho bar, and then the definition of this potentially crystalline kind of deformation ring obtained by kind of taking the closure of the locus inside this kind of max spectrum that has satisfies this condition. So rho GK and QP bar such that rho is, let's say, potentially crystalline of type lambda tau. So that's kind of how these strings what these strings are meant to capture. It's going to give a loci inside the universal kind of deformation ring of rho bar, given by kind of like conditions, periodic Hodge theory conditions on the generic fiber, and takes the risky closure. So it's a bit kind of like indirect. Okay, so the digression. So now I'm going to explain kind of a little bit on what kind of rational periodic Hodge theory condition kind of this word like crystalline with given Hodge weight and inertial type mean. So since it's an algebraic geometry seminar, I will kind of motivate it in the following way. So the slogan is that these are the conditions kind of that the periodic étale cohomology of a smooth proper variety over K has. Yes, where X over K is a smooth proper variety. So I guess in this talk, you've encountered two adjectives. One is kind of like de Rham, and the other is, I guess, like crystalline. And what it meant is that, so a prototypical example of a de Rham GK representation, so the periodic étale cohomology has a Galois action. So the typical prototype example of a de Rham GK representation is exactly just any étale cohomology of a smooth and proper thing over K. And what kind of, so it turns out these Galois representations that they are realizable as étale cohomology of such a smooth proper variety are actually somewhat special among all possible continuous GK representation. And that's because they are comparison theorems in kind of like periodic Hodge theory. So it's an analog of the Betti to étale cohomology comparison theorem for complex variety, where you have, if you tensor with a kind of, you have a larger coefficient to contain enough periods, you can kind of move between different cohomology theories. So the de Rham representation enjoys a special property that if I tensor it up to the de Rham period ring, so maybe just do QP here, it compares to kind of algebraic de Rham cohomology. X over K. So that's a K vector space. And so there's some kind of canonical comparison isomorphism between these two. And already just from this, you see that this has a special property because the de Rham cohomology of X over K has no Galois action. So the de Rham period ring has a Galois action. So this means it's a direct isomorphic to a direct sum of B de Rham S GK reps. Okay, so the reason is because this part of the tensor product receives no Galois action, so all the Galois action has been moved into just the period ring. So it turns out, so this is actually the definition of what it means to be, for general Galois notation, those not necessarily of this form, to be de Rham. So that when you tensor it to some suitable large period, de Rham period ring, you can kind of like trivialize the Galois action to come purely from the coefficient part. And in general, you should think of the de Rham representation as like a prototype, like as basically things that look like the étale cohomology of a proper smooth variety, or like subquotients. On the other kind of crystalline condition is kind of like a stronger condition. It corresponds to the étale cohomology of not just a smooth proper variety, but also a smooth proper variety with good reduction. And kind of, if you want to phrase it in a linear algebraic way, by the same kind of comparison kind of mechanism as the de Rham situation, you have a different kind of comparison theorem. If you have a smooth proper variety of a periodic field with good reduction, there's a comparison with crystalline cohomology of the special fiber instead of the de Rham cohomology of the generic fiber. And it kind of looks like, let's see, so it's going to be the crystalline cohomology of special fiber relative to WK tensor up to B Chris. So here X over OK is like smooth proper model, integral model, X over K. And by the same mechanism, so the crystalline cohomology has no Galois action, so the entirety of the Galois action has been shifted on just this B Chris. And that's, in fact, is a general definition of a crystalline Galois representation. So in either case, I want to explain what it means, what the hot state weights of a crystalline representation means. So namely, if I'm actually like either de Rham or crystalline, the hot state weights come about because the de Rham cohomology of anything actually always comes with a Hodge filtration, and the hot state weights basically just record the kind of dimension of the associate gradient for the Hodge filtration of the de Rham cohomology, and so what is it? So this is like can be organized as a tuple of numbers. And you can kind of arrange them in decreasing order. So here, if the étale cohomology has dimension n, I would get tuples of decreasing numbers, and I get one for each embedding of k into QP bar. Okay, so that corresponds to the fact that, so secretly, just like over the complex number, if I have a variety defined over kind of like some subfield, let's say some characteristic zero field, to compare like, I mean, there are many different kind of algebraic de Rham cohomology. When I have base change to C, I have to embed my field into C. And this is kind of similar here. Okay, so this is what the hot state weight is going to be. It's going to be like a tuple, decreasing tuple of integers, kind of labeled by the amount of embeddings of your field K into an algebraic closure. So this is the kind of like definition of what it means to be de Rham or crystalline. I will also comment a little bit on a variant on what it means to be potentially crystalline. So this would be, in this kind of paradigm here, would be modeled by the étale cohomology of, let's see, the étale cohomology of an X, always smooth and proper, but not quite having good reduction, but rather having good reduction over an extension of K. Good reduction over something like finite extension, which I may assume it's Galois. Let's say Galois. And in this case, you will get a crystalline kind of comparison kind of statement like this, not over the original field K, but over like the kind of extension L, because you only have your integral model over L. And then there's a residual kind of like action from gal or L over K. So I will not elaborate on this, but I want to say that this gives rise to a kind of another discrete invariant, similar to the Hodge-State wave, gives rise to like a finite image representation of the inertia group of K to QP, maybe Q bar to be safe, which has finite image. So it factors through the inertia group of L over K. And this is extendable. So this is what's called an inertial type. So it kind of records this, the role of this kind of finite image representation is to record exactly the failure of being crystalline, like to record like what is the minimal amount of the field extension I can make to acquire good reduction. And that's kind of like its geometric meaning. Okay, so that was a kind of digression of what this actual periodic Hodge theory condition means. They came traditionally from this sort of periodic Hodge theory, the geometric part of periodic Hodge theory, where you try to understand what structures there are on the étale cohomology of smooth proper varieties of a periodic field. But why is it relevant for this kind of Langlands reciprocity kind of story? So the relevance to kind of the Langlands reciprocity is because most of the time, frequently, the Galois representations that you people know how to construct out of automorphic reps are kind of like automotivic. So Galois reps constructed out of an automorphic rep usually, and in fact, well, conjecturally always, but practically usually motivic. In the sense that you really get the Galois representation associated to an automorphic rep by finding a clever kind of variety over the number field over the number field, and then you can take its étale cohomology and kind of do clever operations on it. So the very construction, therefore, means that the kind of this global Galois representations you would kind of restrict to the composition groups of P is realizable inside some cohomology of some usually smooth proper variety over the local field. And so that's why it has to satisfy this sort of periodic Hodge theory condition. Because, for example, anything in a smooth cohomology or smooth proper variety is actually Dirac. Okay. So this is all well and good. Let me just say that like the study of the local moduli of the kind of just Galois deformation, the universal deformation ring, and kind of like all this kind of quotient of it coming from with periodic Hodge theory condition is basically the kind of key ingredient in the kind of Taylor-Wiles kind of style of approach. And I will not comment much on this because I will stay purely on the Galois side today. But the basic principle is that the Taylor-Wiles kind of method gives you a way to kind of like aggregate spaces of kind of automorphic forms into like modules over this ring, and whose support is like factoring to various quotients like this. And so these modules have kind of lots of kind of rigid conditions constraining them, and so a sufficiently kind of good understanding of geometry of this sort of rings will allow you to prove kind of modularity. That's kind of like Taylor-Wiles method in the nutshell. But so this is kind of very powerful, but there's for many kind of applications, it turns out that it's desirable to have much more kind of geometry in the situation. The problem here is that rho bar is really like a complete local Noetherian ring. So it's kind of like, it's just a local modular, or formal modular. And so the kind of geometry that it supports is kind of limited. So this supports very limited kind of geometry. I mean, it supports more geometry than a point, but in some sense, maybe not so much more. Okay. So in recent years, there's this idea that you should be able to kind of like algebraize this formal moduli into a true moduli of local Galois representation. And so here we want to kind of like algebraize it. to something closer to like traditional like geometric objects like an Artin stack or something. And this actually has been achieved in the last few years. And this is kind of the content of the following theorem due to Emerton and G. So I'll please read through it. So it turns out there exists a formal algebraic stack X over spoof of the formal spectrum of O, my coefficient ring of integers of my coefficient ring, such that, well, it has two properties. The first is that if I look at like finite type points, like the FP bar points of X, this exactly are in bijection with isoclasses of mod P Galois rotation, rho bar from GK to GLN FP bar. Second, it interpolates this formal moduli, like all these deformation rings of rho bar, in the sense that these deformation rings here are naturally the versor rings of this formal algebraic stack at R bar, at rho bar, which are the kind of speaking like the finite type points. So this kind of like algebraize this kind of universal deformation ring. But before, we also not just have the deformation ring, but rather also like all these sorts of portions of it, parameterizing kind of things with periodic Hodge theory conditions. And this also algebraize. So for each kind of pair lambda tau, a Hodge state weight and an inertial type, there exists a periodic formal algebraic stack, X lambda tau inside X, which has the following properties. It's, I should say it's flat, P flat, periodic formal stack, such that its kind of ZP bar points correspond exactly to lattices in potentially crystalline JK rep with Hodge state with lambda inertial type tau. So in particular, this property is implies that like our previous potentially crystalline deformation rings also algebraize to this kind of stack X lambda tau. So they are versor rings to this stack. Okay, so that's kind of like the theorem. So this is the theorem about the existence of a more kind of like global moduli of like periodic Galois rotations. And so this is the kind of moduli spaces of Galois rotations with its periodic Hodge theory locus that I really want to kind of study in my talk. So important warning. So despite the name, so the first is that, so this X is the kind of global moduli of, like say, like n-dimensional periodic GK rep, but it actually, the construction is necessarily kind of subtle because what it actually does not really parameterize. Does not actually parameterize like actual Galois representations. So where I is an O algebra, it's not an Artinian algebra anymore. So that's the difference between local and global moduli. In local moduli, you are only allowed to use Artinian test rings. In the global moduli, you can allow to start evaluating all sorts of more general kind of rings. So, so this is necessarily so because, so the basic reason is because you don't want random representation of a profinite group because the group GK has topology. So you really want the continuous representation of GK. And the basic issue is, unless A is Artinian, it's not clear what kind of topology you put on GLNA. So basic reason is the notion of continuity of rho doesn't make sense. And this is the reason why it took a long time to kind of figure out the right kind of thing that serves as a global moduli of GK rep. So I would not say very precisely what the solution here is. The basic idea is that you can, instead of actually parametric Galois representation, you turn it into a more semilinear kind of object, which is another part of periodic Hodge theory that works integrally. And then you have the definition of the stacks were actually like as moduli spaces of those kind of semilinear algebra objects. And it turns out those actually come in algebraic families, whereas like continuous kind of GK representations do not. But it has a good feature that over Artinian kind of test rings, the two notions coincide. So that's why, like this is a kind of, this is a kind of like global stack whose versor ring recovers a previous Galois deformation ring. But its meaning from kind of more algebraic test rings is kind of much less related to Galois representations. Okay. Any questions? So I move on. So what I want to do now is I want to, so one of the main aims of my talk is to kind of like describe some things, some pieces of information that we know about the geometry of the stacks and the kind of methods that kind of we use to get those kind of results. Before that, let me just list the kind of basic, some rudimentary geometric properties about the stacks that you know of. So this is more or less already came from like Hamilton and G's book. So first of all, the kind of moduli of all Galois representation has relative dimension, like the degree of the field times n squared. So n squared here really should be taught as the dimension of the Lie algebra of GLN. That's a group where my Galois representation lands in. The underlying reduced stack is now not a point, unlike the universal deformation ring, but it actually like is interesting. It's a union of a finite union of Artin stacks over F, and the dimension, it's equidimensional, and the dimension is kind of the degree of the field times n minus 1 over 2. And the way you should really think about this is the dimension of the flag variety, dimension of the GLN. So, the n, what I mean is this portion here is the dimension of the flag variety. And kind of how many irreducible components there are, it turns out that this is parameterized by some modular representation theory. So you have one irreducible component for each irreducible characteristic P representation of the finite group of Lie type GLN K. So this is like GLN of a finite field. And there are finitely many of those. And so this will be called shell weights. Okay, so this is the general properties of the kind of all moduli of GK reps. For the ones that are kind of potentially crystalline, you have some more. So the first thing is that the generic fiber is regular. So it's more or less you think of this generic fiber as smooth. And the relative dimension of O is now kind of smaller than the full thing. So it's this quantity. So what is this? So remember that the Hochstedt weights, lambda, is actually like, you have like one decreasing tuple of integers for each embedding of K into QP bar. Each tuple of integer gives rise to, well, a partial parabolic in GLN. Basically, it's a partition. So it gives rise to a standard parabolic type from the iota. So basically like block upper triangular matrices, where the size of the blocks are kind of like given based on like how many equalities there are among this kind of like less than equal to, greater than equal to signs. And like this is and for each of this, you get a partial track variety and you sum this. So in particular, if like lambda iota are always regular, that means that like all the inequalities are actually strict, then the relative dimension is actually, again, the dimension of the flag variety times. Okay, in this case, the parabolic becomes the upper triangular quadrant. So note that there's a coincidence. So in this case, this dimension agrees with exactly the dimension of the underlying reduced stack of X. The relative dimension agrees. Okay, so these are some very rudimentary geometric information about this stack. And in general, it's very hard to actually go much beyond this. It's very difficult to kind of like understand geometry here. Especially the potential crystalline ones, because there is for two reasons. The first thing is that X lambda tau is just like with the deformation ring, is defined as a flat closure. As a flat closure from some, well, characteristic P local, characteristic 0 locus. And so this has no modular interpretation. Another way you can think about it is that it's cut out by taking closure of some rational periodic Hodge theory condition. So this is an issue about integral periodic Hodge theory, that we don't understand it as well as rational periodic Hodge theory. And the second, also fundamental issue is that it turns out that x lambda tau will be intrinsically complicated. It's intrinsically complicated. And this is a point that I will now elaborate on. So the basic issue is that if your object is complicated, you can't hope for a very simple description of it because there's the conservation of complexity. So let me illustrate this point here. So here's a slightly more, like one of the most kind of basic questions you have given this information about irreducible components and so on and dimensions is the following. So x lambda tau was a p-adic formal algebraic stack, which means that when you reduce mod p, I've destroyed the kind of topology of the formal stack. And this now is just a usual, like an arctic stack. And therefore, it can be taught as basically just a thickening. So it's a thickening, a finite order thickening of the underlying reduced stack of kind of the X itself. And we remember that this was the union of this irreducible components. So you can ask one of the most basic questions that you can immediately ask is, what is the cycle of this kind of special fiber in terms of Z sigma? So let's say it's A lambda tau sigma Z sigma. Was this some kind of like non-negative integers? Okay, so the basic question is, what are the A lambda tau sigma? So let me draw a picture. So first of all, note that there are infinitely many choices of lambda and tau, but only finitely many kind of like sigmas. So the picture you should keep in mind is kind of like this. So each lambda tau gives you some kind of blob, some kind of like lots and lots of different things that are completely disjoint in characteristic 0. But kind of when you go to, so this is over F and this is over E. So if you take the special fiber, they're all kind of like supported in just a like fixed finite union of stuff. And you must be full dimension. So kind of each of this thing will be kind of like some of this irreducible component counted with multiplicities. So it's sort of like this. Okay, so this multiplicity basically records like how thick the special fiber is from the point of view of like building it out of the irreducible components. And so first of all, because there are infinitely many of these different things, it means that there must be a lot of kind of a coincidence happening. So all these special fibers in this countably infinite collection of kind of cycles must all be spanned by in a finite dimensional kind of like abelian group, namely the free one generated by the C sigma. So there must be lots of relations. And the question, so there's a conjecture way to like answer, a conjectural way to kind of get to the question. So to do that, let me introduce some notation. So for each lambda and tau, I can associate a kind of representation of a compact periodic group. So W lambda minus eta times tensor tau is a rep of GN OK over QP bar. And what is it? So this is a locally algebraic representation. So this is the algebraic rep with highest weight. Well, I have a tuple. So lambda iota n minus 1 for each embedding. So this gives you a representation of GLN OK. And this thing here is a kind of like finite dimensional, just a finite dimensional rep of GLN OK. And because GLN OK is compact, this representation factors to a finite dimensional, in fact, irreducible representation of some kind of quotient of GLN OK modulo like P to the n, some large enough n. Okay, I will not actually say what this recipe is. This has to do with the so-called inertial Langlands correspondence, but I will give one kind of simple example later. well, actually in 5 minutes. Okay, so whatever this is a locally algebraic representation of GI and OK over QP bar. And the conjecture is the following. So this is the geometric Roy-Mazar conjecture, which basically gives you a reduction of this problem, this kind of infinitary problem, because there are infinitely many lambda and taus, into a kind of more finitary problem. Namely, that there exist necessary unique effective cycles, Z sigma, one for each share weight sigma, such that everything else decomposes into those. So the cycle of the special fibers of this potential crystalline stack decomposes as the sum of some representation theory multiplicities, m lambda tau sigma of the Z sigma. So this is running over all sigmas. So where the m lambda tau sigma is the multiplicity of sigma in, so there's an important discrepancy. The kind of W lambda minus eta tensor sigma tau is a representation characteristic 0, and sigma is a representation characteristic P. So I should reduce this mod P. So this is a well-defined thing because the group is compact, so I can choose a lattice that's stable under the action, and then I take the mod, I guess here I should do mod bar pi. Mod bar pi reduction and semi-simplify, and the simplification is independent of the choice of lattice. And so I can extract the multiplicity of the irreducible factors. So and that's what this number means. Okay, so let me now give several comments. So the first comment, so maybe let me call this equation like Bm for Roy-Mazar. So the first remark is that this is like a massively kind of overdetermined system. So Z sigma is overdetermined by the system of equations Bm, because there are, as I said, there are infinitely many choices of lambda tau, whereas there's only finitely many sigma. So you're having like you're trying to solve infinitely many linear equations in finitely many variables, and you can show that this system must have maximal rank. So the Z sigma will be uniquely determined if they exist. So the real question is whether they exist. The second thing, let me see to make sure I don't forget anything. So the second thing is that this reduces our basic kind of multiplicity question, reduces question. So the question of, question was it? The question of here, the question of determining this multiplicities into like a finite question, to just computing the kind of intrinsic kind of multiplicity. So kind of like this. So computing how these cycles decompose into physical irreducible component. So that's now a finite thing. And the third thing is that this conjecture kind of predicts that the special fibers become very, very complicated. It's very complicated. In particular, it predicts that this, in general, as you make lambda and tau become large in some sense, these multiplicities will grow very large. And that means that the special fiber is highly non-reduced. So remember that the generic fiber of this thing was actually regular, so it's smooth. But the conjecture predicts that when you reduce it to mod P to get the special fiber, it becomes extremely complicated. Okay, so that's because the multiplicity grows a lot. And here's a basic example. So for simplicity, I just work with chi equals QP, and the tau is like tame, so that it's of the form like, let's say it's of the form a direct sum of, direct sum of Teichmüller lifts of mod P cyclotomic character, mod P cyclo. In this case, the kind of inertial Langlands correspondent of tau has a kind of simple description. It's exactly a principal series representation. So induction from the finite Borel to the finite GLN of like the Teichmüller character on the Borel, raised by the same exponent. And So the representation has a simple construction. However, the behavior in mod P is rather complicated. So mod P sigma tau decomposes into, so here's a table. So when n equals 2, you generically, so I guess generically, decomposes into like 2 generated factors. For 3, you can go to 9. For 4, decompose into 88 characters. And for 5, well, I will not tell you what it is, but it's more than 1,600 characters. So the number of factors is a lot larger than n factorial. So it grows very rapidly. And kind of Janssen has found a generic decomposition pattern for the sigma tau. And second is the multiplicity. So in this case, lambda is eta. So lambdas are given by some kind of periodic Kashtan-Lustig polynomial, which is some like elaborate combinatorial gadget. So it's kind of fairly complicated. So in other words, like this kind of stack here must be sufficiently singular in order to kind of contain inside it this much kind of modular representation theory multiplicity. Okay, so let me now state some theorems. So the first theorem I want to state is joint work with Levin-Murrah, which basically is where we kind of like partially construct some of these Z sigmas in the conjecture. So we can construct Z sigma for sigma sufficiently generic in some representation theory sense, such that this system of equation holds for let's see, for tau tame. That means tau was a representation of the inertial group. Tame means it factors with the tame inertia, and sufficiently generic relative to basically the lambda, the Hodge-State weights, and also the ramification index of K over QP. Okay. In particular, one can show that the cycles we construct must agree with the correct ones that the conjecture would have predicted. So this would be the correct kind of like conjecture, the correct cycles. So that's the first term. The second term I want to state is like a joint work in progress with myself and Tony Feng, is that like for those generic Z sigma, we can find a rather complicated combinatorial formula. Can find a combinatorial formula for how it decomposes geometrically. Combinatorial formula. E sigma equals some sigma prime, C sigma prime. And combinatorial here means in terms of the combinatorics of the FN Hecker algebra. Which is not completely surprising because this modular multiplicities, well, where did I, like this, are also related to the FN Hecker algebra. Okay, oh, I have 5 minutes left. So let me try to convey quickly, like what is the kind of like key tool set that's behind like this sort of theorems. And in fact, the tool set is just probably the more kind of useful thing than the theorem, because there are many kind of other geometric questions that are opened up by having this tool. So the key tool is that we develop a kind of local model theory for this kind of potentially crystalline stacks. Okay, and what does it mean? What does a local model theory mean? It means that I write down a kind of different kind of moduli space that are in some regards simpler to understand than the stacks, but locally in some suitable topologies, they're kind of the same. So let me try and define the local model. So I will, for simplicity of notation, stick to the case QP, and I'll define several objects. So the first is a loop group. So I define it based on the functor of point. So these are functors over O algebras. So this is just the standard loop group. Here n of the Laurent's polynomial, so Laurent's series ring in variable v plus p. Inside that, I have the kind of twisted positive loop group given by, so it's twisted because it's not the standard loop group. If I only had this would be the standard loop group. but I want kind of, it's sort of Ivahari in the V direction. So I mod V is upper triangular. Okay, so from this, standard construction is I can take the quotient of the loop group by the positive loop group, and this is a twisted FN Grassmannian. So it's twisted in the following sense. The generic fiber of it is the standard FN Grassmannian. So it's just a loop group of GLN modulo the positive loop group. But the special fiber, so this twisted positive loop group in characteristic P becomes Ivahari. So this is actually the Ivahari mod the loop of GLN of F. This is over E. And this is the FN flag writing. So this is a kind of degeneration from the FN Grassmannian to the FN flag writing. So to get the model, let me write down just an equation. So let me write nabla tau to the following condition. So if I is in the loop group, I want the equations that d vdd v I inverse plus I, let's say I tau I inverse has at most log pole at minus p. So I can phrase it like this, as inside 1 over v plus p times the Lie algebra of the positive loop group. Here I tau is some, oh, was there a question? Okay, so I tau is some constant diagonal matrix. Constant as in not having the loop variable coming from tau. And that's how it depended on tau. And so basically the local model for the situation is the following object. So M lambda tau is exactly the closure inside the twisted FN Grassmannian of the locus that lambda tau cuts out in the kind of Schubert variety corresponds to the kind of co-character given by the Hochstedt weights. So this is inside the generic fibers of the Grassmannian. Okay, so now I can, so that's the object. So whatever it is, it's kind of defined in a much more group theoretic fashion than like the moduli space of local Galois rotation. It's very closer to linear algebra, or maybe affine linear algebra. So the key, one of the key tool in the proofs of the theorems I stated before was the following theorem, and I guess I'll finish by stating it. So it's the same set of author. So namely that this is Zariski locally as a stack isomorphic to like a quotient of M tilde nabla tau modulo T given by conjugation action, where what is M tilde lambda nabla tau? Well, M lambda nabla tau is something inside the kind of twisted FN Grassmannian. There's a kind of natural torus cover over it, and I just pull it back here. But then this quotient by this torus action is by a different torus action. So what the theorem means is that this potential crystalline stack is kind of like Zariski has an open cover, where each open chart is isomorphic to an open chart inside this quotient stack. Yeah, and that's kind of like the main tool. So if someone asks, I can like describe an examples of how the stacks look like in some low dimensional situations. But I finished my talk here first.
Yeah, thank you very much. It's a very interesting talk. So we have time for questions or comments. Not very much.
Generic, so finish generic means like, okay, so that's a good question. So in the first term, so here, so the sufficient generic here is, so let me say like this. So genericity is theoretically explicit, but not practically. But not practically. In the sense that the genericity is kind of basically, there's going to be some explicit polynomial in characteristic P that the kind of like highest weight of sigma will have to avoid. And the polynomial comes from basically the desire of making some like generic base change statements to work. So since these are explicit algebraic variety, if for any given thing, like for example, by like GL7 or something, you can run it on a computer and find some polynomial that does the job. On the other hand, it's not like I have an explicit combinatorial formula for it. So it's, in this sense, it's kind of like theoretically explicit, but not practically. Also, we do conjecture that this should work with actually rather mild genericity condition. And I mean, there's some hope that like the methods I use in the second theorem will eventually be able to prove something along these lines, but we are not kind of at that stage. Yeah.
Okay. Yeah. So very stupid question. So how about the possibility of apply this to the program you posted at the very beginning of the talk? I mean, about the correspondence.
So, I mean, it does give some global applications, but no, it doesn't give. It's not sufficiently strong to give like Langlands reciprocity in that new case. It was strong enough to kind of solve what's called the weird part of shared conjecture in many cases. So that's like the question of like if I have a mod P local system on say a modular curve, when does when does a system hacker eigenvalue contribute to it? So that kind of question in its generalization is called the weird part of shared conjecture, and like our theorems actually prove like this kind of GLN version of that conjecture by exactly performing this sort of program, basically by just like looking at the spaces of like mod P cohomology of locally symmetric space. You just patch it and you get like sheaves on this moduli space of Galois rotation, and then just use our local model to control what kind of sheaves you get. So that's so the quick answer is it's not kind of strong enough to prove something like reciprocity, but it does prove various other kind of statements of global nature like this.
Okay, yeah, okay. Yeah, thank you very much. So we should stop here because of the next talk. So we'll resume in 10 minutes. Yeah, for the second talk. Thank you, Bao. Again.
Okay. Bye-bye.